So let's take a closer look. One of the things we're going to do today's lecture is look at other stars being born. And this is actually a cute little stellar nursery. Okay, so now the nebula wouldn't look this cool, like the sword part in Orion, but with just binoculars. But even with just binoculars, you can see this fuzzy green looking thing. So you can see this with binoculars. But what we're going to do is we're going to zoom in. And zoom in a little bit more. Okay, and I'm going to go ahead and add the labels. Believe it or not, that actually is a stellar nursery. So all those kind of circles are where stars are being born. I know. So even though our star was born about 4.6 billion years ago, you're like, how do we know what we're talking about? Well, we can see other stars in the process of being born, okay, in other nebula. So again, we can see other stars in the process of being born. These are what we call protostars. Okay, so they're not really turned on yet. Okay, but we think this is kind of what our star went through. Can you kind of see the disk region? So this black is because the star's light, or the protostar's light, is too bright, so they blacked it out. And so we can kind of see this disk. This disk around, it's a protoplanetary disk. I think I used that term before. This is where planets can form. Are there planets around other stars? Yeah. Yep. Okay, so there's that, the nebula. In nebula, there's other stars being born. Another thing, before we talk about kind of the formation of our planets, we need to remember that there are two types of planets. Okay, that's probably one of the things you already knew before you came in here. Of course, we have the rocky planets, starting with Mercury through Mars. Okay, then we have the gaseous planets. Okay, starting with Jupiter through Neptune. So here's why they are different. So the nebula that actually formed our sun and the planets was composed of this stuff. There's 4 things that the nebula was composed of. First off, there was helium, hydrogen. Actually, the conservation of matter, there still is helium, hydrogen. So you're like, relatively speaking, is there a lot? Yeah. Okay. 98% of our current solar system, hydrogen and helium. I don't know about you, but I know that life needs carbon, life needs oxygen, life needs hydrogen. Fine. Okay, but other than that, I don't really care much about hydrogen, especially helium, although there is a helium shortage now. Did you know that? Little kids all around the world are upset because helium has skyrocketed. And years ago, they used to have like a national reserve for helium, and then they broke, there's like, oh, we don't need it anymore. Probably somebody's making some money on it. But helium is actually a very rare gas, and once it's gone from the Earth anyway, back out into the solar system. So only 2% of our stuff in our solar system and the stuff in the solar nebula is not hydrogen or helium. So I want you to kind of pay attention to this column right here. This column right here says, at what temperature will that stuff, there's 4 things, at what temperature will that stuff go from being a gas to condensing? You know how water condenses in clouds? You know, you see a cloud milky white because water has gone from a gas to a liquid, and it rains maybe. Okay. So notice that the hydrogen and the helium will not condense. This is important because the hydrogen and the helium in forming our planets, it's not a player as far as it will not condense. So now we go on to compounds. You know, what is a compound? Basically 2 atoms that are stuck together in a repeating unit. Water's a compound. So hydrogen-containing compounds, water, methane, CH4, contains hydrogen, it's a compound. Ammonia, NH3. Okay, so there was 1.4% of our original solar nebula, and still today we've got that stuff floating around in our midst. Okay, Notice that that will condense, but it has to be 150 Kelvin or colder. Otherwise, it's a gas. Okay. I'll go ahead and put the other two up together. Because honestly, if you're like me, when I kind of think of us, if I think of us here today, walking around, I kind of think of these. But notice they are in abundance of 0.6%. You're like, really? I'm like, really? Okay. Various rocks and minerals and metals just in general. And notice what temperature they need to cool down to in order to condense. Notice that they will go ahead and go from a gas to a liquid and or a solid. They begin at least kind of coming out their gaseous stage at temperatures as hot as, 13 Kelvin, 1600 Kelvin. Okay, so the point here is it can still be kind of toasty, and this stuff will go ahead and quit being a vapor. So we can make some planets, basically. Okay? So I'm going to introduce something here called a frost line. And basically the frost line, one way to think of the frost line that I'm going to talk about is basically kind of being between where stuff is going to condense out. Okay, even if it's these compounds are going to condense out, or if it's hotter on this side, too hot. Too hot for compounds. I'll put CPD for compounds. Too hot for compounds. Frost line, this stuff can condense. Okay, and the whole condensing thing is important to get a plant. So that's how that all fits in. So I'll go ahead and play this for you. Too hot to condense, but not too hot for compounds to condense, but not too hot for metals to condense. So the way you read this is over here is the sun, okay? And let me go ahead and scroll this down. So here's the sun, and here is getting farther and farther from the sun. So these right here, this one, that's where the Earth is. That's 1 astronomical unit. So the way this works is I could click up here, 1 astronomical unit or so, and it went ahead and put me a point on how hot that is. When I get closer to the sun, you think it's going to get hotter or cooler? Hotter. It is going to get hotter. Okay, so I'm closer to the sun, it's getting hotter and hotter. So I get farther out, it's going to get cooler and cooler. So I'm going to kind of click some points. Okay, so this is the cooling temperature. This is the hot temperature. Now if I go ahead and add some summary details, you see the green line? Basically, closer than the green line, everything's going to be a gas because it's too hot. Okay, it's kind of like Goldilocks in the Three Bears. Okay, after the green line and clear out to the blue line, your metals and your rocks are going to go ahead and stop being a gas and start behaving so they can become a planet. Okay. Local-wise, you have to get beyond, this would be what we call the frost line. Beyond the blue line, that's where you can go ahead and get your ices. Your methane, your H2O, your hydrogen-containing compounds can go ahead and stop being a vapor because finally or start being a vapor because finally it's cool enough out there. Stop being a gas. Okay, so that's how that works. Okay. So there's this frost line that kind of differentiates between the inner rocky planets and the outer gaseous planets. So the thermometer is kind of showing you the inner thermometer. It's hot, but it's not so hot that your metals and your rocks are not going to condense. Okay. So inside, you're going to get that. Granted, it's a small fraction of what our solar nebula is, but it went ahead and early on, in the early part of our solar system, time in our solar system, went ahead and condensed. Okay. Then out there, the best we can do, or I should say, we can go ahead and get metals and rocks condense, and we get ice. so we kind of have this sweet spot beyond which, on the inside, all we get are rocks and metals. Over the frost line, they can pick up ices. So you figure, and I have a slide to kind of emphasize this, but you figure then if you can go ahead outside the frost line and start picking up those hydrogen-containing compounds like water, methane, and ammonia, if you can go ahead and start building planets when it's cooler out here, your planets can get awesome big. And actually that's a factor in Jupiter, Saturn, Uranus, Neptune being so darn big, because they had privy to more stuff. So the rocky or terrestrial planets, the inner planets, okay, toasty, kind of close to the sun. And again, the only thing that really could go ahead and not be a gas was our rocks and metals. And it's kind of nice, even though here in the Midwest we don't have tides, what we do have is snow. So, so when I think of like planet building, I kind of think of making a snowball. It really is very similar. Okay, so basically the stuff in, this is the solar nebula. Okay, so kind of the stuff in one track, kind of over time, like 100,000 years, basically kind of snowballs together. We call it accretion. It got bigger and bigger. Gravity kind of kicked in. Little ones joined big ones and that sort of thing. Okay, so you see a term here, planetesimal. I love that term. Okay, planetesimal is basically not quite a planet. Okay, so again, if you want to go back to the building a big snowball, it's possible that you build a medium snowball, somebody else builds medium snowballs, and then you combine those snowballs together. That's kind of the process. I think it's kind of hard to make them stick. That's kind of the process. So still talking about talking about both types of planets. Okay, so you kind of see the green region inside, it's too hot for anybody. Okay, from the green to the frost line, you can go ahead and get your planet formation, your rocky planet started. Okay, and then in that red region, that's where you can actually get your gaseous planets forming. So the way this animation works, if I remember right, is I can click somewhere and it will show you what's going on. So like I'm going to click in the green region and it said, try again, too hot, too close to the sun. I'm going to click in the other region where I better reset. Let me click in the region after the green but before the frost line. Okay, and there's a little movie down there. And it will show you. Okay, those nice little gray particles. Can you almost see the whole snowball making a big snowball? Blah, blah, blah. Give it 100,000 years and you'd be surprised. Okay? So I'm going to reset this. And those particles, this will be metals and rock. Okay? I'm going to reset this and you'll see the different color. You'll see blue here coming in. So this would have been how Jupiter, Saturn, Uranus, and Neptune. Don't they seem like they could be bigger, badder? Okay. And the thing about the giants, okay, the gaseous giants, the Jovian planets, is they actually, when they got big like this, they had gravity on their side. So then even though helium and hydrogen isn't going to condense, helium and hydrogen's like, dang, I'm going to respect this planet, and it's gravity, I'm going to hang around. So that's how that worked. Respect your planet. So you see a few words. You see planetesimal, kind of the precursor to a planet. Protoplanetary disk, just kind of looking for terms for your test. You also see the term accretion, building a snowball, kind of that's what that is, getting bigger and bigger. So kind of from left to right, you see kind of the plane of the ecliptic, by that. Kind of all the planets, and this is like over time, all of the planets orbit the sun in a plane, okay? But early on, there were a lot of, I call these crumblies, and there are still some of these left. Man, last night, have you guys seen some shooting stars recently? dang, right that up. No, I don't think there's a meteor shower, but it's like, I saw one last night that just went like forever. And I pointed out to my friend, and I'm like, dude, look at that. So anyway, there are still some of these crumblies left. But a lot of them found homes as planets in a planet, okay? So this is kind of what I was saying about the Jovian planets, that I like the animation we looked, because now not only did they have the gray particles, but they also had the blue particles, which was the ices from the hydrogen-containing compounds. They got big enough to go ahead and hydrogen and helium stuck around. Been there ever since. Unlike the planet Earth, that if you let helium go on Earth, it's gone. Balloon and all. Now, the balloon will eventually blow up and latex will fall to the Earth, but the helium's gone. All right. I think we're okay with that. Well, this is kind of fun. And actually, I know it says sun, but I'd like to kind of say maybe proto-sun there more appropriately, because in a minute we're going to talk about proto-sun. We're going to talk about how when the sun turned on, which I would have loved to have been there, I think, or just see it, like Doctor Who, he could go back and see it, okay? But when the sun began nuclear fusion in its core, basically it had this positive pressure we call solar wind. You might have heard of solar wind before, and it went, okay, all in one, just crazy. So to me, it looks like it's not turned on because I don't see it kind of clearing kind of the dust from its region. But if we kind of go out a ways, pretend that's Jupiter, okay? Pretend that little kind of insert there is Jupiter. Jupiter actually has its own system of moons. And I think we've looked at, like, Io is one of Jupiter's moons. Galileo saw 4 moons orbiting Jupiter. And so it's kind of like it has its own little, I won't say plane of the ecliptic, but it has its own little frisbee out there. So this process of accretion actually can happen around here. I need to pick a different color, don't I? It actually can happen in different tracks there. Isn't that cool? So it has its own little mini system. All of the gaseous planets have moons. All of them. Does Mars have any moons? Yep, I know. But is Mars, what's different about Mars moons? Do you remember?
When you said they were ugly moons.
Yeah, I said they're ugly moons. Mars moons are ugly. They look like potatoes. Has 2. Does Venus have any moons? Oh. Venus has no moons. Mercury, no moons. Earth, a beautiful moon. Mars, 2 ugly moons. And then these guys, all moons. Yeah. Okay. Oh, I like this one. So I said kind of how when the sun turned on, and I like the whole Doctor Who thing. Okay. So this little animation is going to show us how kind of when the sun turned on, it created this solar wind that kind of swept out the gas anyway. It kept the planets intact, thank goodness. Okay. So here we go. And we'll talk about how stars are born. Okay, but that's it. Actually, it kind of showed the arrows stopping, but the arrows are still going on. Okay, I'll do it one more time. It's like what I call positive pressure in all directions, not just the plane of the ecliptic. So honestly, the sun's been doing that ever since. It's like it's associated with kind of the radiation. The sun's doing that. So one way to think of it is if like a little nasty microorganism from beyond our solar system wanted to get in, it would have to kind of swim up that solar wind. I think that's kind of a fun thing to think about. So that solar wind's been going on ever since. And actually, the Voyager spacecraft that are leaving our solar system, the one way we know that they've left our solar system is we don't see that solar wind. Basically, they're out of here. Anyway. Okay. So there's this slide again. Kind of from left to right, you have over time kind of accretion making objects larger and larger. Planetismals would be like the middle one. Ooh, look, this one's got action. to kind of talk about the leftovers. The leftovers that, in a chapter coming up, we're going to talk about meteors. Kind of has rocks fall through the Earth's atmosphere and create that streak. Okay. So one of the things we know, because evidence is there to support it, is that early on, and you can go to that middle frame, because you had like lots of crumblies, medium number of crumblies, and basically no crumblies clear here today. But early on, there was miscellaneous stuff. I like to think of it as like very chaotic. Okay? And so there were a lot of more hits than there are now. And those hits had consequences. Honestly, among other things, those hits, we think, gave Earth its water. Okay? How else did we get our water? Because honestly, remember, Earth is too close to the sun. It's too hot to have H2O come out of its gaseous phase. So how did we get it? Well, icy rocks from on the other side of the frost line chaotically travel in and out, okay, still orbiting the sun, and hit the Earth and deposited our water. There was an article or a podcast I listened to recently, Sci-Fi, Science Fridays, and they talked about how the water on Earth is older than the sun. You're like, really? So I listened to it, and it actually talked about, it was neat, really what we're talking about today. It said that, you know when I showed the solar wind, the like that one? Okay. So basically, the water that's associated with the Earth was created before that. And that's what we call the birth of the sun. So they're like, water is older than the sun. That's cool. Okay. So, things, chaos in the early, what's going to be our solar system. Lots of crumblies. Lots of bombardment. Actually, can be the reason why Uranus used to have its axis of rotation, like straight up and down to its orbit about the sun, and now it's like that. Okay? We said Venus actually goes like that. Okay, so that hit kind of gives credence to what we're talking about. Kind of crumblies that might have been in the early part of our solar system could have ended up as captured moons. These look like the moons of Mars. Okay, and I'm pretty sure this is Phobos and Deimos. I don't know which is which. Panic and fear around Mars. Okay, just like leftovers. So the early chaos in our solar system actually gave us our moon, and this is how it happened. So I'm going to kind of draw your attention to three kind of different frames up here. This one's first. Okay, what this is showing you in, I've heard it called, I want to say Theia. There's a name for this impactor. So what you see is Earth, who's started to form. It did the whole accretion thing like it's supposed to, right? Okay, and then you see, because of the chaos, an impactor about the size of Mars. Okay. Number 2 down here, okay, if you read it, actually, this hot thing now is the Earth. It's hot because it just got smacked by Theia. Okay, and can you kind of see the stuff kind of streaming off of the Earth? This stuff is going to form the moon. Okay. Basically, given enough time, that stuff, and you can kind of see it down here, that stuff turned into this stuff. And it kind of reassembled. So here's the deal, and there's actually, when we talk about the moon in more detail, what makes up the moon is very similar to what makes up the surface of the Earth. And the reason for that is this precursor, or this impactor, hit the Earth, and what kind of splashed out was what was on the surface of the Earth. Okay, so it's got kind of this old sort of rock to it. So given time, notice we use the word accretion again. The moon basically picks up the little chunks in its orbit and forms. All right. So impactors. I said as much, right? Hopefully you're able to kind of see Uranus's tilted axis of rotation and it kind of spinning on its axis. See the ring of Uranus? So just to kind of summarize what we've been talking about, I know it's hard to see the captions, but you know, kind of step 1, we have the solar nebula. Step 2, we have rotation and contraction. Step 3, we kind of start to have kind of the rocky stuff coming together via accretion. Okay, step 4, kind of more of the same thing. Notice that actually planets, the Jovians, kind of have their own little mini accretion disk. Solar wind, and so can you kind of see the difference between those two? Kind of clearing the dust and making it kind of a pristine, beautiful system of planets around a star that we have today. All right, so let's talk ages. Now, it's funny because when I was thinking about how do we age rocks, I thought about one of the things that we talked about earlier was carbon-14 dating. Carbon-14 dating does not work for rocks in general because carbon-14 dating only works for things that were once alive. So, and we'll talk more about meteorites. Actually, that is a fallen meteoroid. So here's my, bless you. If this is the Earth's surface, okay, and this is the Earth's atmosphere, okay, and this is a space rock up here, okay, that space rock would be a meteoroid, and we'll talk more about this later, meteoroid, kind of like an asteroid, a meteoroid, okay. When it falls through, if it's lucky enough to fall through the Earth's atmosphere, it will create a streak. That's my streak right there. The streak is the meteor. And if there's anything left that you can pick up, okay, here's my little happy person who found this rock, space rock. If anything survives, that is a meteorite. Okay, so that is kind of my, in a nutshell, meteoroid, meteor, meteorite. So meteorite is a space rock. Just make sure it's not a meteor wrong. Get it? Meteorite, meteor wrong? I know. There's a knack, and it's like a chemical assay to say, if you pick up a rock, you're like, did this come from outer space? Well, take it to somebody who has the tools to test it. Okay? But we do know that we've had space rocks come this way. If you ever see a meteor shower, if you ever see meteors, you're like, I wonder if a rock survived. Okay? So we can date those. And this is a busy slide, but you've all heard of elements like special K. You've heard of potassium. And you've also heard of argon. Okay? So what this is trying to tell you is that basically, and remember we talked about atomic mass numbers? Mass numbers are basically telling you what isotope of this particular form of this element is. So isotope 40 for potassium, isotope 40 for argon. Let's see if I can find that. But you see on the periodic table, I haven't, see, K is potassium. And we said that 19 means it has 19 protons in it. Okay, how many protons does argon have in it?
18.
18, yeah. Okay. So basically, it has the same mass number. So maybe it converted one of its protons into a neutron. I'm liking that. A little radioactive decay. So what rocks will do and have been doing ever since our sun turned on is converting their potassium into argon. So bottom line is you know what you're looking for, you know the rate of decay, and so you can date meteorites, meteorites. So this is a meteorite. You can kind of see the flecks of material in there, iron-like material. And so this would date, using that isotope dating, to 4.6 billion years old. So that's when our sun turned on. Kind of cleared it, yeah, 4.6 billion years ago. So I usually say 4.5 or so billion years old is how old our solar system is. Okay. So one last topic I want to cover is the planets that orbit other stars. Okay, so you're like, really? How does that work? How do we know that? And there's a few ways to know that. One is, and actually this isn't another star, this is our sun. What this says is if you were over here on a planet orbiting another star, you could look at our sun and you would see our sun wobble. If it was kind of in the right plane, right vision, you would see our sun wobble. And you know our sun is wobbling, or our sun is wobbling because it's being orbited by a large planet. There's a tug of war going on, okay? So that's one way we can tell that, or somebody could tell that we have a planet Jupiter. There are direct ways, though, that's indirect. There are direct ways to basically know that there's a planet up there. This one says that you, in a limited sense, sometimes you can actually see the planet. The planet, let's see, I don't know, it's been 2 weeks now, but basically, did you guys hear that they have seen the signature for water from a distant planet? It's like a planet orbiting another star. They see the signature for water. And I bet they use spectra, like those spectral lines, to see fingerprint for water. So that's direct. And the example I showed you with kind of Jupiter tugging at the sun, that would be indirect. And that's most common. So people much more patient than I am are doing this sort of stuff. Okay. So I got kind of ahead of myself, but in so many words, again, this is saying that if you were somewhere else in our galaxy, probably, in the Milky Way galaxy, looking back at this star, the sun, you would see it move. And this is kind of showing its movement. There's a cartoon out there, I think I told you, about an old lady and an old man in their living room discussing the sun, and the old lady's looking out and saying, the man's saying, is the sun still there yet? She says, yep, still there, because it's converting its mass, right, to energy. And we could also do that with this one, say, is the sun moved? Oh, it's still the same sun, but it is moving. So another way to indirectly tell it's there, and this has to do with the tugging, because I'll go over here again. Remember, I'm on a planet far, far away. Okay, in our planet orbiting another star, looking back, and I said you could see the sun wobble, okay, like this. But what if the plane of the ecliptic was such that actually the sun was wobbling like this? Okay, the same thing, getting tugged by a planet. Okay. In that case, what we would have to use is the Doppler effect. Okay, we would actually see a blue shift when the sun's going towards us and a red shift when it's going away from us. So you'd see the wobble that way. And that's one of the things we talked about, kind of something moving towards us, a blue shift, something moving away from us, a red shift. So years ago, back in 1995, they found their first extrasolar planet. An extrasolar planet means a planet around something that's not the sun. Okay, and since then they've been finding them right and left. So before 1995, if you had taken this class, the possibility of finding planets around other stars, you're like, I don't know. So another way, and again they're calling this indirect, but another way is that if a planet is orbiting a distant star, that planet will have an effect on light coming from that system. So what you see, for instance, at positions 2 and 3, when the planet goes, now again, this would have to be kind of a directional thing, because the plane needs to be kind of in our line of sight. But at positions 2 and 3, when the planet goes in front of the star, you're going to see the light from the star dip down. Why? Because the planet's eclipsing, okay? Actually transiting, okay? Then the other thing is when the planet goes behind the star, positions 5 and 6, you're going to see a little dip there because that planet gave you a little bit of light. A little bit. Cool. You may have, if you're like transit, I've heard that term before, okay? So here's the deal, and I'll put a little heart there, because the transits I think of, have you ever heard of the transit of Venus? Venus transit? Basically, when somebody says that a transit of Venus is occurring, we're back to our solar system, right? There's the sun, and I'm on the earth, and basically Venus is going through our line of sight for the sun. That's a transit of Venus, and it's a wonderful thing to watch. So you need a solar scope, but you can see Venus going across the face of the sun. So again, things have to kind of line up just right to kind of see for these indirect methods. You know, the Doppler effect, kind of the eclipsing effect. This again is trying to kind of block out that intense light coming from the star, and some happy person is pointing up there to, that actually is light coming from a planet right up there. Isn't that cool? Okay, so just to kind of wrap things up too then, maybe you've heard in general, planets tend to be, the planets they first found anyway, they're finding more closer to Earth-like, but the planets they first found were the giant gaseous planets, okay? But now they're finding some kind of more like Earth. So when we find a planet, scientists find a planet, they kind of categorize it with regard to how long it takes to orbit its star, how close to its star it is, okay, the shape of its orbit, how massive is it, and its density. Of course, density gets to, is it a terrestrial planet or is it a gaseous planet? Kind of what it's made up of. I don't know if this link will work or not. Click at it. Yeah. So one of the spacecraft, or one of the telescopes, I guess I should say, a telescope that's orbiting the Earth is it orbiting the Earth or is it orbiting the Sun? Lagrange place. I'll have to find out. But Kepler is a telescope, and it is designed especially to look for planets. Okay. And it's been up there for several years. I'm thinking it's no longer working. They're just kind of crunching data that Kepler gave us. So each dot, this is like a really busy sort of graph. The size of the dot represents how massive the planet is. And so you kind of have the scale up here to show masses relative to, what do you think the subscript J is? Which planet of ours could that be comparing it to? Jupiter, yep. So basically, if it's the size of Jupiter to 10 times the size of Jupiter, you have that next to this one right there. So you can kind of see with regard to size. The other thing is you see here how close it is to its star. Okay, and then here you see how eccentric is its orbit. Remember kind of that Kepler said that the planets orbit, our planets, orbit the sun in ellipses, and we talk about kind of how oval or how round it is. So we see, I think, and I've heard others say, the reason there's so many massive planets is that they are easier to see. But kind of drawn to scale, you see our solar system on there in green. So I said they've kind of, as of mid-2010, so that's dated. Gosh, we're pushing 2015. Can't believe that. So you can kind of see in this kind of bar graph here, relative sizes. Okay, notice we're kind of on the heavy end. Pictures say a lot of words. So what planet is this one? Saturn, yay! And this could be Uranus or Neptune. Blue. Probably Neptune, I guess. Okay, so again, this is kind of dated. But notice when they, there are some anomalies, some things that have scientists scratching their heads with regard to, for instance, a planet that's as large as Jupiter being close to the star. You're like, how does that work? Because that's outside of kind of what we just discussed today. Is that my last slide?
That's the end of it.
Okay. Very good. Well, that's it for today. I know it went fast. For Monday. So this chapter will be due on Wednesday. Wednesday, we're going to start in on planets. So we basically just have Wednesday, Friday, Monday for the planets. So the test is scheduled for a week from Wednesday. You're fine. A week from Wednesday. And it might be Friday. We'll just kind of see how the material goes. Okay.